Okay, thank you very much for this kind invitation. Yes, and somehow I prepared a long talk, and I doubt that we will come to the end of this talk. Yes, but we will see how long we will go. But I prefer to go slower than to rush to the end.
Mm-hmm.
Okay, so therefore it's good to ask questions. Yeah, so this talk is about quantum graphs. By quantum graphs, I understand Schrödinger operators on metric graphs. And they are defined by the following construction. This is a triplet. That first you take a graph. This is a metric graph. So all the edges are intervals of a real line. On these intervals, you have a differential expression. Today, we are going to speak only about magnetic Schrödinger operator. There are two potentials: usual potential, electric, and magnetic potential. Yes, at the vertices, you can put some matching conditions or vertex conditions. Today, we are going only to speak about standard conditions, which mean that the function is continuous at every vertex, and the sum of derivatives which are taken in the direction outside the vertex is equal to 0. The first condition is continuity, the second is Kirchhoff condition. Yes, and all the graphs today will be formed from finitely many compact edges. Therefore, the spectrum will be discrete. And one will speak about these two spectra. One is the Schrödinger spectrum. This is the spectrum of the Schrödinger operator. It's an eigenfunction that satisfies eigenfunction equation on the edges and vertex conditions at the vertices. And the second spectrum is spectrum of the standard Laplacian. Sometimes I'm going to say that this is a graph spectrum because it is uniquely determined by the metric graph. And I can make an advertisement for my book somehow. Everything that you will not understand, you can read in the book, which is published and it's open access. Okay, so I already told you that it's a finitely many compact edges, so that all the eigenvalues are discrete. The lowest eigenvalue is non-degenerate. All other eigenvalues may be degenerate, but they satisfy Weyl asymptotic law, where capital L is the total length of the graph. And this problem is very special for specialists in inverse problems, first of all, because there are eigenfunctions that are not supported by the whole graph. There are eigenfunctions that are identically equal to 0 on certain edges. It's not clear that sometimes they don't exist, but they may be present. Then I already told you that the lowest eigenvalue is simple. And for example, if you have Laplacian, then corresponding eigenfunction is just a constant. And the spectrum alone, in general, does not determine the graph and the potential. So, and there exist isospectral graphs. These are graphs that have the same spectrum, even without any potential. So, for example, Vyacheslav Pivovarchik, who is listening to this talk, he constructed a lot of simple examples of such graphs. Okay, so as usual in inverse problems, one may start with Ambertsumian theorems. Yes, and the classical Ambertsumian theorem says that if you have an interval and then you have a Schrödinger operator with a certain potential Q, and if it happens that the spectrum of this Schrödinger operator with potential Q and standard conditions, but standard conditions in this case means Neumann conditions at the endpoints, because continuity means nothing, and there is only one derivative which appears in Kirchhoff condition. So this derivative must be 0. This is the Neumann condition. So it happens that if these eigenvalues are the same as for the Neumann Laplacian, Neumann operator with zero potential, then the potential is zero. So, and one can prove different results for these graphs. For example, first one can prove some kind of geometric version of this Ampersand theorem. It tells the following, that if you have a Laplacian on a certain metric graph, and the spectrum of this Laplacian is the same as the spectrum of the interval of the same length, of the same total length, but you see, you can see it from the Weyl asymptotics. Weyl asymptotics determines the total length of the graph, yes? So if you have a Laplacian that has the same spectrum as a Laplacian on the interval, then your graph is an interval. And this has been proven by different people, at least what I know 4 times, and I still like our final proof. It also brings something to the problem to understand. But you can also generalize this to the following theorem. For example, if you have a Schrödinger operator, so with some potential on the graph, and the spectrum is the same as the spectrum for the Laplacian on the interval, then the graph is interval and potential is zero. And in principle, I can tell you how to prove this, but maybe shall we skip it because, or is it interesting? Will somebody hear how to prove this? So you see, the situation is the following, that the spectrum of the Schrödinger operator is asymptotically close to the spectrum of the Laplacian. This is the same as for the interval. But the spectrum of the Laplacian is given by a trigonometric polynomial. And in this case, it means that this trigonometric polynomial should have a spectrum which is close to integers. Yes? And this is possible if and only if it really coincides with the integers. Yes? In this way, we prove that actually if this equality holds for a certain potential Q, then it also holds for the Laplacian on gamma. Yes? It means that we can apply the previous theorem and tell that our graph is an interval. And then classical Ampersand theorem implies that potential is zero. One may also mention here similar result by Brian Davis, who using heat kernel estimates proved that if you have a graph with certain potential and the spectrum is the same as a spectrum for a Laplacian, then the potential is identically equal to zero. It tells you nothing about the graph. It tells you only about the potential. Okay. So, but my interest in these graphs was connected very much with the trace formula. This trace formula has been proven also by several people with different order of rigor. Yes. So our final proof is rigorous completely, and it has the following form. Suppose you have a Laplacian on a certain metric graph gamma. Let us denote the eigenvalues of the Laplacian by kn square. You see, all eigenvalues of the Laplacian, they are positive except the zero eigen. Yes. Then on the left-hand side, you put delta function at the origin, and then delta functions at points kn and minus kn. So it means that the left-hand side, especially if you remove this beta 1, you can move it to the right. So then the left-hand side is completely determined by the spectrum of the graph. Then on the right-hand side, you would have this beta 1 times delta with minus. This is the Betti number. Betti number characterizes how many cycles you have. Then the total length divided by pi, and then the sum over all periodic orbits on the graph. So, and here you have lengths of periodic orbits. This is L of p. This is the length of the primitive orbit. So it means that if you go along the same orbit several times, then you only take the basic orbit, the length of the basic orbit. And this is the product of scattering coefficients along the orbit. So it means that the right-hand side is determined by some topology, geometry. The left-hand side is determined by the spectrum. And in the original formula, this term, beta 1 delta, was on the right. But now we prefer to put it to the left, because then this formula has a remarkable feature that on the left you have a sum of delta functions, but on the right-hand side you have a sum of exponentials, because this is a constant. Constant is a trivial exponential with frequency 0, and cosine, this is also a sum of two exponentials. And you see, if you think about this Fourier transform, then one should probably think that if you take a Fourier transform of the right-hand side, you will also get a sum of delta functions. So this is a remarkable sum where you have a sum of delta function, and its Fourier transform is again a sum of delta functions. And this is very unusual. So, and we have done a lot in this direction. This is connected with so-called crystalline measures, but this is not what I'm going to speak about today. Today, probably the most interesting thing is that this formula is a direct generalization of the Guillemin-Melrose trace formula for manifolds. So which says that if you take the same cosine over the Laplacian eigenvalues, yes, then it's equal to the sum over closed geodesics. So this is very similar to the formula that I have. The only difference is that this formula has some kind of correction term, and about this term is not the only thing which is known, that this is L1 log function. Yes, and actually this L1 log function turns out to be beta 1 times delta function, but in many practical applications, delta function can be seen as a L1 log because you can integrate it. So it means that this is a direct analogy of this formula. Okay, so from this formula, you can derive a formula for the number of cycles. Beta 1, this is the Betti number. This is almost the number of cycles in the graph. Simply by taking, if you know all the eigenvalues of the graph, these are lambda n, you take square roots, you take sinus k divided by k square, and then it's important that you divide by a certain parameter t, yes, and then you send this t to infinity. So let us check that this formula is reasonable. So you see, this lambda n, they grow in accordance to Weyl asymptotics. This lambda n, I don't know how to, lambda n here. They grow like square, yes, n square. So the square root is n, then n square is n square. The square of n will be n square. So it means that this series is converging for any t. there is no problem, because all the elements, they decrease like constant divided by n squared. But if you try to take a limit sending t to infinity, then this cosine, the argument goes to 0, it will be 1. And here you have also sinus something small divided by small, it also goes to 1. So it means that each term in this sum goes to 1. So it means that if you exchange limit and summation, you will get infinities. So you cannot exchange it. Yes. The interesting thing in this formula is the following. That first of all, here instead of Laplace eigenvalues, you can put Schrödinger eigenvalues, because Schrödinger eigenvalues are very close to Laplace eigenvalues, but the first eigenvalues don't play any role, because you can split this sum as a finite sum plus the rest. And the finite sum, you can exchange the limit t and summation, and you will get the same result. Okay? So it means that it works also for Schrödinger operators, for Schrödinger spectrum. So it means that all isospectral graphs should have the same number of cycles. Yes, this is the first result. The second interesting result is the following. Making some numerical experiments, we established that actually in order to reconstruct the number of cycles, it's enough to know about 20 or 30 eigenvalues. You don't need to know thousands of eigenvalues. It's enough to know the first 20 eigenvalues if your graph is not very complicated. Because here you don't need to go to the limit, because you know that beta 1 is an integer. Therefore, you may start going to the limit and then cut this infinite sum to finite, and get this number of cycles. This was surprising. Okay, now I'm going to speak very general about inverse problems for metric graphs, and putting this problem as most general. So what does it mean to solve inverse problem for Schrödinger operators of the metric graphs? It means that you need to reconstruct everything. First of all, you have to reconstruct the metric graph. Then you have to reconstruct potential Q and potential A on the graph, and then vertex conditions. I told you that I'm not speaking about vertex conditions today at all. So therefore, the last part removes. And also this magnetic potential, instead of reconstructing this magnetic potential, yes, I will use it to solve the inverse problem. Namely, for graphs with cycles, I will consider spectral data which depend on the fluxes of the magnetic field through the cycles. Because if you have this magnetic potential, you can eliminate it on every edge. But eliminating it, you have to go around every cycle, and then you will see that you cannot remove it if this integral is not the integral that I have here, this phi j. If this integral, which is known to be a flux of the magnetic field through the cycle, if it is not equal to 2 pi times integer, yes. If it is 2 pi times n, you can remove this magnetic potential. If not, then you cannot remove, and the whole spectrum will depend on these fluxes. Yes. So, and then you can use the following idea that you consider your spectral data depending on these fluxes. So, and in this way, they will help you to solve the inverse problem. And I will jump between two notions connected with this graph. One notion will be M-function. This is generalization of Titchmarsh-Weyl M-function. And the second is response operator. And the idea is to reduce the graph, to make it smaller, using dependence of this spectral data on the magnetic fluxes. So let me explain what is it and how to do it. So if you have a graph, then on the graph you pick up several vertices. You have to pick up all vertices of degree 1, yes, and maybe some other. But the idea is to not to take all vertices, but observe that any point inside the edge can be considered as a vertex of degree 2. Okay? So, and these special vertices will be called contact vertices. The idea is that you can approach your graph through these vertices. Okay. I told you that there will be spectral data will be two things, either response operator or Titchmarsh-Weyl M-function. And they are connected via Laplace transform. So the Laplace transform of the response operator is equal to the M-function. So let me explain this in more details. What is the response operator? So the response operator is defined as follows. You consider the magnetic Schrödinger wave equation on the whole graph, on all edges. You impose standard conditions at all vertices, not contact vertices, inner vertices, yes? And you impose only continuity condition at your contact vertices, yes? Then you have zero initial data, yes? But you prescribe the value of your function on the boundary, on these contact vertices. So there is some kind of boundary control. So you can prove that the solution is unique. So one can think about the formula that you take this graph and you shake it at these contact vertices. Yes. So the solution is unique. So, and then you can calculate the derivatives at these contact vertices. By derivatives, I mean the sum of all derivatives, yes, at these contact vertices. So this is the response operator. If I shake only one point, for example, then I will get non-zero derivatives at all other contact points. So it means that this is a matrix response operator. And then also I will have such effects that when I shake one point, I initiate a wave, which will penetrate through the graph, and then after a while it comes back. So how this could be seen? So this response operator can be characterized by a kernel, by a certain kernel, yes, yes. This kernel depends on the difference of the times due to causality, yes. But this kernel will have the following property. First of all, you have some diagonal matrix times the derivative of the delta function, but this is like what is left from the wave that you sent into the edge. Then there will be some smooth terms. This is the reflection from the potential P. But then after a while you will get waves that reflect back from inner vertices, so some delayed delta functions, and also coming from other contact vertices. Because if I shake one vertex, then the wave goes through this graph to any other vertex as well. Okay, now I speak about Titchmarsh-Weyl M-function. What you do? You consider stationary problem. You consider stationary Schrödinger equation. Yes, in the lambda is in the upper half plane. You impose standard conditions at all non-contact vertices and only continuity condition at contact vertices. No Kirchhoff, no condition on the derivatives. But instead, you prescribe the value of the function at these on these contact vertices. And this solution is unique, so you can again calculate the derivatives. So the M function descends the values of the function at contact vertices into derivatives. So it's the same as Titchmarsh-Weyl M function. The only thing that in Titchmarsh-Weyl M function you have just one interval, the real line. And M function sends the value of the function into derivative. Now you have values of the function in different contact vertices into corresponding derivatives. And these such problems involving this Titchmarsh-Weyl M function, they have been studied by Gelfand, Levitan, Marchand, and recently there was an approach by Simon and Gestesi. So what are the main theorems here? The main theorem about response operator is due to Avdonin, Belishev, Korolov, who proved that if you know response operator for the Schrödinger operator equation on the half line for certain time t, then it determines potential on the interval from 0 to t over 2. This is exactly the interval which is covered by the wave, which goes inside this interval and comes back during time t. It managed to go on with this. Similar result for M functions is by Gestesi, Simon, Ram, who proved that if you have a Schrödinger operators with equal potentials, but potentials which are equal on a near the origin on some intervals from 0 to a, then the difference between the corresponding M function is O capital of this exponential. So it means that the difference is exponentially small. So it means that if you have two M functions which are exponentially close, then the corresponding potentials are equal on a certain interval close to the origin. No? And equivalence had been noted by Sergei Avdonin and me in 2008 and described in detail by Rybkin later on. So these approaches are completely equivalent. Okay. Now I need to give you also a little bit more. I want to give you two formulas, explicit formulas that determine these M functions. And this is formulas in terms of the eigenfunctions of two Schrödinger operators on the graph. You see, with the same graph, you can associate two different Schrödinger operators. One is standard operator. Standard operator is when you put standard conditions not only at these internal vertices, but also at contact vertices. Yes. The second operator is Dirichlet operator. This is determined by standard conditions at internal vertices and Dirichlet conditions at contact vertices. So these two operators are self-adjoint. There are corresponding eigenfunctions, which denote them, these eigenfunctions, by psi n standard and psi n d. So, and then I derive two formulas that determine M function. The first formula, it uses eigenfunctions of the standard operator. You take their traces on the boundary. We need to take normalized eigenfunctions, but look at their values on these contact points. Yes, and then you plug it in here, and in the denominator you have difference between your spectral parameter lambda and the corresponding eigenvalue. Here you have -1. So one can say that this Titchmarsh-Weyl M-function has zeros at the spectrum of the standard operator, because this function that we want to invert has a singularity there. Yes, it has a singularity, but then you take an inverse. It means that M function has, in some sense, 0 at this point. And analogous formula for Dirichlet eigenfunctions, it's a little bit different. So there is no inverse there, but we cannot determine the M function directly, but we only can determine the difference of this M function in different energy parameters, lambda and lambda prime. For example, you can put lambda prime equal to 0 is one possibility. Okay. And then you have a formula which is C. So this is completely analogous to this one. You see, now you look not at the traces of these Dirichlet functions on the contact vertices, because the traces are 0 by definition, because these are Dirichlet eigenfunctions. But you look at the derivatives in the same formula, and now the singularities of this is at the Dirichlet eigenvalues. So it means that the singularities of M function at the Dirichlet eigenvalues, and zeros are at standard eigenvalues. So, do you have questions? Does somebody have questions? I think Boris.
Any questions?
No?
Let me see.
No, okay. So then we continue. Okay. So we are going to use these functions very much, but they have one disadvantage. We're going to use these formulas very much, but they have one disadvantage, that there are eigenfunctions which are invisible. Because, for example, you may have eigenfunctions, standard eigenfunctions, that are 0 on these contact vertices. Then you don't see them in this M function. And the same may happen here, that you have Dirichlet eigenfunction, which has 0 derivatives. You will not see it either. So these eigenfunctions are called invisible. But hopefully, the ground state is always visible. So you can prove it by hands, because the corresponding eigenfunction cannot be equal to 0 on any edge. Okay, so inverse problems for trees has been solved by so-called peeling procedure. And maybe I just explain with the picture. You see, suppose you have a tree, and you know M function for this tree. Yes, M function is connected to the response operator. Yes, if you know response operator, you know traveling times between different vertices. Yes, if you know all these traveling times, you can reconstruct the tree. So traveling times, they can be used to reconstruct the tree. Very good. Moreover, from this response operator on any edge, you can reconstruct potential on this edge. So you look at this bunch of edges, and you reconstruct potential on this edge, and on that edge. And then, instead of looking at response operator, you start looking at M function. Because then, knowing M function for this big graph, you can calculate M function for this smaller graph, where you cut away this branch. And then you just continue. The idea is you go from big graph to a smaller graph. And then you repeat this procedure. You take another bunch, reconstruct potential, cut it away, you get a smaller graph. Again, and then you finally come to just one interval. So the problem is solved. So what to do with graphs with cycles? So here we suggest to use so-called that we call it magnetic boundary control. It means that we are going to consider all objects like response operator or M-function not only as a function of the spectral parameter lambda, but also as a function of fluxes. And actually, you don't need to know it for all fluxes, but only for fluxes 0 and pi. This will be understand later. So the idea is to reduce everything to trees, to dismantle graphs into pieces that look like trees, and then then we can solve the problem. And our solution of the problem is generic. So it means that under some mild conditions, the problem can be solved. But we don't formulate this as like for almost all graphs, this method gives a solution. No, we formulate these conditions explicitly. These conditions, if the graph satisfies these conditions, 1, 2, then if we have a solution of the problem. What is very important that the proposed method is non-destructive. So it means that in practice, if we want to solve the inverse problem, we don't need to cut away edges physically or attach boundary control at many vertices, like it has been done by other authors. No, just sometimes it's enough to have control only at one vertex. I will show you there. Okay. First of all, if you have a graph like you see on the left, so this is a compact core, and then there are some branches attached. To branches, we can apply method of peeling method. For trees, it was local. So it means that we can, knowing M-function for the left graph, we can calculate M-function for the right graph. So everything is solved. So it's enough to look at the graphs on the right. So here is an example how we can dismantle graph. For example, we have a graph on the left, yes, and the red vertices are situated so that if we cut our graph at these vertices, we are getting a set of trees, yes? So it means that we put so many contact vertices so that cutting at these vertices, we get trees. And you see, for example, there was no need to cut here because it was a tree anyway. But anyway, we put too many. So how to make a reconstruction here? So it is based on this lemma that every Dirichlet eigenfunction on a tree is visible. Yes, so you can prove it by and then okay, maybe we go simply to the next. So you see, if you have this P graph with these contact vertices, yes, then the M function is equal to the sum of the M functions which correspond to each piece. Yes. So the only thing that we have to do, we have to split our M function associated with all contact vertices to M function corresponding to each of the pieces. Yes. For example, how can I see the M function corresponding to the first? You see, the ground state eigenfunction will always be visible, because I told you that the ground state eigenfunction can be equal to 0 identical. So it means that I will see singularities of big M function associated with certain vertices, and then I see that this is M function associated with the first part of the graph, yes? But then all eigenfunctions are visible, so it means that in the future I pick up from M all singularities that are associated with these vertices. And then I continue. Then I look at the next singularity, which is not connected only with the first one, and pick up and put into M2 all the singularities that correspond to this path, and so on and so on and so on. Since the graph is finite, I can decompose M into finitely many M functions corresponding to each piece. So here I will need this condition that different pieces don't have the same eigenvalues. But this is a condition which is generically satisfied. This explicit condition. And then I can divide big M function into M function corresponding to the subtrees, and then I solve inverse problem for each of the subtrees, and then I have to glue it back together to reconstruct the whole. So this is the first solution of the inverse problem by dismantling. I dismantle the graph into pieces, but then I need a lot of M functions. The other idea is to dissolve a vertex. It goes in the following. Suppose I have a complicated graph, which is green here. And then this graph has one vertex of degree d0. Yes. And I want to, from M function for this graph, calculate M function for the graph where I split this vertex into, in this case, 4 degree 1 vertices. Yes. So how can I do this? I can do it using these magnetic fluxes, because in order to do this, I have to cut exactly d0 minus 1 cycles. Yes. So let us look at the formula. The formula for the M function for this left graph, yes, is given through M function for the right graph. So here you have, in that case, there will be 16 smaller functions. They are connected to the fluxes. So the flux is this Fi minus Fj. This is the flux through the cycles, yes? And then you can see that looking, for example, at the singularities, you can reconstruct what you can reconstruct. These are just simple calculation. You can reconstruct the absolute value square of the eigenfunction, the sum, yes, and also their product of these derivatives, yes. So the idea that we need to reconstruct from this information, we need to reconstruct singular derivatives. We need to reconstruct these derivatives one by one. So we know the sum of squares, and we know the products. Yes, and this can be done if we have at least 3 vertices coming together. Why 3? Because you see, if you have 2 numbers, a and b, in a square plus b square and ab, then this information doesn't determine a and b. You will get a quadratic equation to determine a and b. But if you have 3 or more numbers, for example, a square plus b square plus c square, and then the products ab, bc, and ac, then you can determine A, B, and C up to multiplication by -1. But this doesn't matter because multiplication by -1 it's the same as multiplication of the eigenfunction by -1. It doesn't change the eigenfunction. Yeah? So it means that we prove the following thing. If suppose that there is a graph gamma, the big one, and gamma prime, this is smaller graph, dismantled graph, graph with the dissolved vertex. They're connected. And the vertex has degree d0, which is greater than 3. Yes? Then if I know the M function for the big graph for all magnetic fluxes, then this M function for all magnetic fluxes for the original graph determines d0 times d0 block of the M function for the graph gamma prime, provided the spectrum of the Dirichlet operator on gamma prime is simple, generically satisfied, and then every Dirichlet eigenfunction should have at least 3 non-zero derivatives. But this is exactly for this reason that I just explained. So how can we apply this theorem? Suppose we have this graph, and I know, and I have only one contact vertex, the red one. It has degree 3, knowing M function for all magnetic fluxes, I can reconstruct M function for this graph, but then I can peel out these edges, because there I can reconstruct the potential, I know their lengths and so on, can take them out. So now I have a new graph with now 3 contact vertices. So if I take now this vertex V prime, I can do the same, yes, and get M function for this graph. I took away these edges, so I have a new graph, yes, and here I can continue dissolving this vertex, and I'm getting a tree. I reconstruct completely. So if I take here wrong way and dissolve V star, then for this graph I'm coming to a loop, and then I don't know what to do, because here all contact vertices have degree 2. So it means that sometimes it goes, sometimes it doesn't go, and it depends on the topology of the graph and whether we are clever enough to choose the correct way, or we will lucky. So you see, with every graph, when we try to reconstruct the graph starting from one single vertex, you will get some kind of infiltration domain. This is the domain which can be reconstructed. Here, this is an example. This red graph we can reconstruct. We can reconstruct potential in the graph there, but then we are facing degree 2 vertices, and we cannot proceed. So we know nothing about the graph outside this green area. Yes. So this is another example. The bottlenecks, they are very dangerous, because if there is a graph with bottleneck, then usually you cannot go through this graph. You can only reconstruct part of the graph, but you cannot reconstruct the rest if you start from this vertex V0. So this is infiltration domain. Here is another example, which for me it was interesting, because if you start from V0, then this graph generically can be reconstructed. Cannot be reconstructed, because you come here to a degree 2 vertex, and then you cannot proceed. But if you start from the right, you come here, And then you have a degree 3 vertex, you can reconstruct it. So starting from the left vertex, we cannot reconstruct, but starting from the right, we can reconstruct. Okay, one can formulate general theorems telling that if your graph is such that all infiltration domains, they cover the graph, then you can reconstruct the graph and so on. But somehow I don't want to speak about it because I think that it's better to leave some time for the questions. Because I think that my picture there, they provide the idea of it. Yeah? Okay, so I just want to make another advertisement for that. If you have questions about this, read my book. So I have a new hobby, checking how many times it has been done, and now it's coming close to 100,000. So I think that after this seminar it will reach 100,000. Last time I checked, it was 94. Okay, thank you very much for your attention.